In this video, we're going to discuss proof by contradiction. So let's suppose that P and Q are logical statements. A proof by contradiction of P implies Q proceeds by assuming P and not Q. So you assume the hypothesis P and you assume the negation of the conclusion Q, and then deduce a contradiction. What does it mean to deduce a contradiction? Well, it means that you have to find another logical statement, R, and prove that P and not Q implies R and not R. You see, R and not R is a contradiction. That's sort of the standard logical form of a contradiction. And the statement R, it's something you have to find. So it makes proof by contradiction a little bit tough in the sense that you've got to search for the right contradiction, but it is a powerful proof technique, and we'll see an example of it. This proof technique is based on the fact that P implies Q and P and not Q implies R and not R are logically equivalent for any logical statement R. To see that, observe the truth table for P implies Q is the same as the truth table for P and not Q implies R and not R. It's the same in the sense that given the same inputs for the truth values of P and Q, you get the same outputs for the truth value of P implies Q as you do for the truth value of P and not Q implies R and not R. So in particular, if P and Q are both true, then both P implies Q and P and not Q implies R and not R are true. The only case where they're both false is when P is true and Q is false. You can see that they're both true if P is false and Q is true, and they're both true if P and Q are both false. So that means they're logically equivalent statements. And since P implies Q and P and not Q implies R and not R, since those are logically equivalent, if we're asked to prove P implies Q, it would suffice to prove P and not Q implies R and not R. So it would suffice to have the following kind of proof. You assume the hypothesis P, you assume the negation of the conclusion Q, and then you deduce a contradiction R and not R. If you're successful in doing that, then you've produced a proof by contradiction. So let's look at an example of a proof by contradiction. This will involve the infimum of a set F. So let's suppose that S is a set of elements from an ordered field F. An element T in the field F is the infimum of the set S if, first of all, T is a lower bound of S. So if S is an element of S, then T is less than or equal to S. So T is a lower bound. And not only that, but it's the greatest lower bound. And we've formulated that here in 2 as saying that if something is larger than T, then it's not a lower bound. So if something's larger than T, if X is larger than T, then there's something in the set S, there's an element little s in the set big S, such that S is less than X. So 2 exactly says that if an element is larger than T, it's not a lower bound. And that means that, of course, that T is the greatest lower bound. So we'll call this the infimum of the set S. And we want to prove that the infimum of a set is unique. So we'll prove this by contradiction. In particular, we're going to prove the if-then statement. If M1 is the infimum of S and M2 is the infimum of S, then M1 is equal to M2. Okay? And we're going to prove this by contradiction. So let's assume that M1 is the infimum of S, and let's assume that M2 is the infimum of S. Okay? So we're assuming our hypotheses. Now, let's figure out, this has some important consequences for us, that M1 and M2 are infimums of S. It means, first of all, statement 1, M1 is a lower bound of S. Statement 3 says that M2 is a lower bound of S. Statement 2 says if something is larger than M1, then it's not a lower bound. So if L is larger than M1, there exists an X in S such that X is less than L. Okay. So if something is larger than M1, then there's an element of the set S that's smaller than L. And 4 says that if L is larger than M2, there's something in the set S, there's an X in S that's smaller than L, so that X is less than L. Okay, so those four statements follow from our assumptions that M1 is an infimum of S and M2 is an infimum of S. Now we're going to assume, by way of contradiction, that M1 is not equal to M2. So the proof, what we're trying to prove is that if M1 is an infimum and M2 is an infimum, then M1 is equal to M2. So we assume the hypothesis, M1 and M2 are infimums, and we assume the negation of the conclusion. So we assume that M1 is not equal to M2. And we're going to try to find a contradiction here. Now by trichotomy, we have two cases if M1 is not equal to M2. Either M1 is less than M2 or M2 is less than M1. So let's take these in cases. Let's first look at the case where M1 is less than M2. In other words, M2 is greater than M1. So now we're going to use our properties of M1. Since M2 is bigger than M1, and M1 is an infimum of S, we know by fact 2 above that there's something in S smaller than M2. Okay? Remember, M1 is an infimum, so anything larger than M1 can't be a lower bound. So there's something in the set smaller than it, right? So that means there's X in S so that X is less than M2. Now, on the other hand, we know that M2 is a lower bound of S. So since X is in S, M2 is less than or equal to X. But that gives us a contradiction because by transitivity, now we have M2 is less than or equal to X, which is less than M2. Okay, so that's a contradiction. That means we can't have M2 greater than M1. All right, what about case 2? If in case 2, M2 is less than M1 or M1 is greater than M2, and we just run the same argument. We know that M2 is an infimum, so if something's larger than M2, it can't be a lower bound. In other words, there's something in S, let's call it X, that's smaller than M1. On the other hand, we know that M1 is a lower bound of S, and since X is in S, it follows that M1 has to be less than or equal to X. But that gives us a contradiction because then it says by transitivity that M1 is less than or equal to X, which is less than M1. So in either case, we get a contradiction. So we assumed our hypothesis that M1 and M2 were infimums. We assumed our negation of our conclusion that M1 is not equal to M2. They gave us two cases, and each case leads to a contradiction. Okay, so that means that our assumption can't be true. Our assumption that M1 is not equal to M2, we can't have all these assumptions at once. In other words, if M1 and M2 are infimums, then we have to have M1 is equal to M2. So that's an example of a proof by contradiction. Let's look at this statement that we proved in an earlier video, in the video on proof by contrapositive. We want to look at it and try to do it as a proof by contradiction. So if we were trying to prove this statement by contradiction, we'd do the following. We'd say, all right, let's assume that n times m is even, and let's assume by way of contradiction that n is not even and m is not even. All right. So that tells us that there's a natural number k1, so that n is equal to 2k1 minus 1. And there's a natural number k2, so that m is equal to 2k2 minus 1. Okay, that's the definition of odd. So if n is not even and m is not even, then they're both odd. Okay, so if we multiply n and m together, we can write the product n times m as an odd number. So we get 2k minus 1 times 2k1 minus 1 times 2k2 minus 1. Multiply that out, we get 4k1 k2 minus 2k1 minus 2k2 plus 1. We can factor out a 2 and we get 2 times the quantity 2k1 k2 minus k1 minus k2 plus 1 minus 1. All right. And so this, like we did last time, we need to show that this thing in the parentheses here is a natural number. So we claim that if k1 and k2 are natural numbers, then 2k1 k2 plus 1 is greater than k1 plus k2. All right. And the proof is just like we did in the previous video. K1 and K2 are natural numbers, so they're both greater than or equal to 1. So if we take K1 greater than or equal to 1 and multiply that inequality by K2, we get k1, k2 is greater than or equal to k2. We take the inequality k2 greater than or equal to 1 and multiply by k1, and we get that k1, k2 is greater than or equal to k1. So now if we add those two inequalities together, we get 2k1, k2 is greater than or equal to k1 plus k2. So if we add 1 to the left-hand side, we get something even larger. We get 2k1, k2 plus 1 is greater than k1 plus k2. So that implies that the thing in the parentheses, the 2k1, k2 minus k1 minus k2 plus 1, that implies that thing's a natural number. And so that means that n times m is 2 times a natural number minus 1, which means that it's odd. Okay? And that contradicts our assumption that n times m is even. Now notice that we set this up as a proof by contradiction, but we haven't used our assumption that n times m is even until the end. Okay? It turns out that this proof is not really a proof by contradiction. The only place that we used the first assumption was to reach the contradiction at the end. Alright? So really what we proved is that Pn not Q implies Pn not P. Alright? But what we actually did was we proved not Q implies not P. It was only at the end that we used the assumption of P to get the contradiction. So in other words, even though we set it up like a proof by contradiction, it turned out that it was actually just a proof of the contrapositive. Alright? And so it really would be, logically speaking, a proof by contrapositive. And so if you run into a situation like that, where you don't use one of your hypotheses until the very end to make the contradiction work, you probably have a proof by contrapositive and should rewrite it that way so that it's a cleaner proof altogether. So that's it for now on proof by contradiction. Thanks for listening.